today. So Moises Castillo is my friend and also a colleague. He works at the Center for Gravitational Wave Astronomy. He's a graduate research assistant. He works at CTMO as an observer and also as the assistant director. And he's a PhD student at UT Arlington and UTRGV. So his research, he typically works on eclipsing binaries as an observer, and also we work on the optical follow-up of gravitational waves related to work done at the Center for Gravitational Wave Astronomy. So let's introduce our speaker. Let's welcome our speaker, Moises, please.
Hello, everybody, and thank you, Richie. So today's presentation is something that's very interesting for us, specifically in the EM follow-up group, because it means another potential source of how can I say, like a data stream, right? We have data. Something that I've heard a lot of speakers say in the past that do astronomy is that there's a lot of archival data, and this would be a great way to look into it kind of like it's like a slight peek into other things we can look for in archival data. So specifically here, Luminous blue Kilonova, not GW170817, GRB150101B. So the very famous Kilonova discovery that happened was GW170817. So it's 2017 on what is that? August 17th. It was an exciting day. I remember we were here, huddled in your office, my team and Richard, and we were seeing the reports coming in, and unfortunately we could not do anything from our observatory because we were too north in the sky. So things didn't work out for us here, but our collaborators down south had a very fortunate view, right? With a little bit of luck, we were able to see the event. Now, here, this is before, right? So the one I'm talking about is GRB15, so that's 2015, the January 1st. And, well, let's look into it, shall we? All right. My presentation, what it consists of, I have an introduction, talk about what a GRB is, what Kilonova is, the methods that they used, and the results. I myself was learning through all of this, and what I picked up were like the key features of those things related to the paper, right? So that's what I'll be presenting to you, the things that I learned in reading this paper. So that's one thing I want to make clear, right? That this is a learning process for me, and the purpose of these seminars are to be learning experiences for both parties. Right? And yeah, so there's a bit more results that were posted in the paper, but I just, lack of time, I did not get to go through the entire paper, though I really do want to because it's very interesting. All right, so GRB basics. First, GRB, right? What is a GRB? It's a gamma ray burst. Here pictured, you see there's an artist render of a GRB, and I'll explain a little bit more about that right now. So it's an energetic explosion, and it's characterized by a flash of gamma rays and long-lived afterglow. So the following part is the process, right? The process that happens for this gamma ray emission. Here you see that there is a star that's undergoing some nuclear process, right? And you're creating heavier elements. And then the nuclear process stops. There is a huge collapse and a huge explosion, release of energy, and the creation of a black hole. Right. So in the flash, you'll see some gamma rays emitted, and you can possibly also see some stuff lingering around after. I can't say days or years because the time scale for that afterglow is really large. Right? It could be very small or very large. It just depends on the event that happened. So gamma rays, right? The sources. Just gamma rays in general. defined like this, at least in Wikipedia, right? Electromagnetic radiation arising from the radioactive decay of atomic nuclei. So that means it's an atomic process. Right? There's interactions of down to a particle scale. Right? And in astronomy, though, things look a little bit different because we're talking about like these huge things that are very massive, things that either happen really fast or really slow. And when you look at it in that perspective, they refer to as the gamma rays in terms of energies, photon energies, and specifically greater than 100 kiloelectrovolts. So if you receive a photon that is of that much energy, then they say, oh, yeah, it's a gamma ray. But it is possible to have, for example, X-rays that are higher energy. For example, in medical imaging devices, that's an example there. People bring up X-rays to the gamma ray regime in astronomy. Yeah. So those so-called X-rays. Right. And how they are made, there's a hypothesis for the mechanism for the creation of gamma rays, which is inverse Compton scattering and synchrotron radiation of high-energy charged particles. So essentially, we're just talking about high-energy events. If you have a high energy, specifically, like looking at like the inverse Compton scattering, you have an electron that is traveling at relativistic speeds that hits or interacts with a photon. Then some of that energy is then scattered to that photon, which then sends it off with a higher energy. Right? So, and the synchrotron radiation is, I forgot. Yeah, I don't remember what that is. Yeah, I don't know if you can.
I mean, it's basically consisting of accelerated charge particles.
Okay, yeah. And so then this goes into the next part where you will find those mostly at the formation of black holes. Okay. You have again relativistic things happening. So on the border of the event horizon, some crazy stuff is happening. Particles are being greatly accelerated, and you have high energy collisions that happen, right? And then from there, we're able to find these gamma rays that eventually somehow make their way to us. Time ranges. Time ranges for classifying the gamma ray bursts. You'll see sometimes in literature or on like articles and stuff, they use an GRB, GRB by itself, and that's pretty much all I've seen. Though I have seen some conflicting things where they use a lowercase s and an uppercase s, referring to the same thing, right? And that will be something like as a warning if you're ever looking at things in astronomy. Lowercase, or even just in science in general, lowercase is not the same thing as uppercase, but sometimes it is. Right? So you have to be careful. You have to be careful with what you're reading. So short GRBs are bursts that are detected for less than 2 seconds, meaning long GRBs are greater than 2 seconds. Okay? And there is also a mythical creature, which is the ultra-long gamma ray bursts that last over 10,000 seconds. And there are, like to give you the distribution of that, there are about 3 ultra-long detections that have been made. Short gamma ray bursts comprise of about 30% of the gamma ray burst detections, and the long are about 70%.
You said ultra-long 3 as in ever?
3.
3 ever?
Yeah, like 3 measurements, or 3 detections of that. Yeah. At least what I read, you know. There could be others, but I remember only seeing 3 that were there in the documentation that I was reading. Then, so now we're going into Kilonova part. Now we understand a little bit about what a gamma ray burst is. There's a flash of gamma rays, and then there's some afterglow. So here is 2013. It's going to be the first detection of a kilonova, and the way I wrote it was GRB 2013 evidence for kilonova, because there is no there was not very strong, I guess, supporting data that you can have. Though I'm not sure exactly what that would look like, because they have two data points here. Right? This is the Hubble Space Telescope, and on June 13th there's something there, and then on July 3rd there's nothing there, which the time scale at which it happens fits right in with what would happen with a kilonova. Right? So there's a paper that has all this, and they discuss it in great detail. Unfortunately, I did not read that paper in its entirety. I just got to get little parts of significance. So for us, when we do the gravitational wave research, the significance is trying to see the distance of where these events happen. Right? LIGO is limited to the detections based on the masses. We can figure out the distance and the masses of the objects, right? Given the whatever template is that the detection was made that it follows. And then here in this case, this was before the first detection made by LIGO, and the redshift that was calculated for this puts it at about 1,000 megaparsecs, right? Which is completely out of range for even supermassive black holes. Is it? No. It's within range for supermassive black holes before LIGO. But the things that would trigger this are not nearly as massive as that. So we're talking about something that's near a solar mass.
So it's out of the range for binaries or stuff.
Exactly, yeah. So, so this is very far. So in order for LIGO to have been able to see this, and then it would have been difficult, if not impossible, right? All right, cool. So now kilonova. Kilonova is an astronomical transient event. I'm putting this here because I saw the literature make reference to three things. One was a GRB, which luckily I knew what it was, which is gamma ray burst. And then the GRB170817, and then there was AT 2017 GFO. Yeah, I had no idea what that was, so I had to, of course, look up what is AT. AT is an astronomical transient event, and these are different naming conventions that the groups that are looking at these objects in the ranges that they're interested in. Each group then has their own naming convention, right? So it's an astronomical transient event, a kilonova. Why? The groups that do this are mainly, they're the group that looks at mainly optical or around optical. I'm not sure if there are also X-ray telescopes that participate in the group. I forgot what group it was. I'm sorry, but most of the things, like I saw like Pan-STARRS was one of the groups that feeds the database that these astronomical transient events are cataloged. So kilonova, there are two potential ways that they are formed, which is two neutron stars or a neutron star and a black hole merging. Right? And we think back to thinking about where these lights come from. Right? We need some charged particles. We need some high energy. We have collisions happening. It's all the right stuff, right, to get these flashes. And these flashes, they say, they're about 1,000 times brighter than a nova, right? Hence kilonova, right? Like kilo, 10 to the 3. And which is caused by the eruption of a white dwarf, and they're about a tenth to 1/100th the brightness of a supernova. So it's between, it's not a nova, but it's not a supernova, right? So we call it kilonova, right? Cool. All right. So, you guys enjoying the talk so far? Yeah. Cool. That's great. So now's the nitty gritty stuff, right? And this is something that I think I focus more on this part because I'm actively engaged in taking data, right? I want to make sure that the data that I'm taking now is something that could be used by myself, but also my team and anyone else who wants to maybe look back at whatever images I'm using in the future. Or maybe it's not somebody that's looking at the stuff. Maybe it's some automated process, some pipeline that's going through the data that I've taken before. If I have good data, then great. If I have bad data, then I don't know, maybe bad data could be used for something. Right? So gamma rays, they use gamma ray observations, they use X-ray observations, ultraviolet, optical, and infrared, and some information from the host galaxy. The kilonova events are typically found in some area where it's a neutron star, so the galaxy region is no longer producing stars, typically. That was one of the things that they did mention at one of the later parts of the paper. They described the environment, and they'd make some correlations between the gravitational wave event from 2017 and the one that they did the one that this paper describes from 2015. Right? So there's some similarities there. There's only 2, so we need more. It's convincing though. I don't know. So the gamma ray data reduction for the GRB150101B, it was triggered by the gamma ray burst monitor, the GBM, on Fermi satellite was triggered. So that's what sends the notice, like, hey, there's something, right? And what's interesting is that it was found at a later time with the Swift burst alert telescope data. So the burst alert telescope did not find it, like it wasn't triggered. It didn't cross whatever threshold it is that they had set. So it wasn't found. And the same thing is true for integral. So they went back, looked at the data sets, and like, there it is. So it was across three telescopes, but only one was actually triggered for following up with the event. The data reduction, so the Chandra X-ray telescope was used. They did minimization of contamination due to its proximity to the galactic nucleus. So there's the galaxy, and it's bright, right? There's a lot of stuff there that are giving off emissions. And here, there's galactic nucleus, but there's an A. I'm going to point this out. It's active galactic nucleus, right? That's what that typically refers to. But nowhere in the paper do they use an A before the AGN. So I'm just pointing that for you guys. So since it's close to the center of the galaxy, it's a really bright spot, and then you have a flash coming out of that bright spot.
Wait, so the galaxy from this GRB, it was an AGN specifically? It wasn't just a normal galaxy?
Mm-hmm.
Oh.
Yeah, and actually, I don't know what the difference is between a normal galaxy and an AGN. I know the A is for active, but does that mean that it's a star producing? Or?
It means that you have a supermassive black hole inside, which there is some matter spinning on it, and basically the AGN, I think it's something that you see depending on the if you would see this galaxy like that you see only the core is the stream from the supermassive black hole is just towards you, then you will have a blazar, but if you have the AGN, it means just shooting can observe. You can see that this is active. You get the, it's not directly towards you, it's rotating.
But it's not just a galaxy that's big, because an AGN, they unified the model with quasars, so they're essentially the same thing as quasars, but looked at a different angle.
Yeah.
Galactic nucleus, if you're looking just at a normal galaxy, every galaxy has a supermassive black hole, but that one's a high redshift quasar object.
I see.
Yeah,
Okay.
but
That's just why I was making sure,
Yeah.
because I was like,
Yeah.
it's a big distinction.
Okay, no, that's good.
But basically, I made a mistake. It would be a quasar if it would be just directed towards us.
No, you were right the first time. Blazar is, you're
Oh.
down the axis of the jet, quasar
Okay.
is tilted on a high inclination.
Okay. Oh, okay.
Right. Then there is the Swift XRT, the X-ray telescope aboard the Swift satellite. So Swift has different instruments, as you saw on here. It says Swift Burst Alert Telescope, right? And then there's the Swift X-ray telescope. There's different instruments aboard the same satellite. Again, they had to do minimization of the contamination of the AGN and yeah. So pretty much you get the profiles of the galaxies, and then from that you're able to make kind of like you can see the contribution of the fluxes that are related to the galaxy, and from that you can then extrapolate your source counts, if you will. And then we have the ultraviolet, optical, and infrared data reduction. They use the 4.3 Discovery Channel telescope, which I didn't know, and if I'm you can correct me if I'm wrong, but I think if I read correctly, it's housed in the Lowell Observatory. I had seen that somewhere, but I might be completely wrong. But I had no idea. Discovery Channel telescope. That's really cool. And what is the Discovery Channel? Well, that's Disney Channel.
No, I was gonna say every channel needs to have their own telescope now.
Yeah, I mean, this competing telescopes. That'd be great. I think there could be a market for that, right?
So this is at the Lowell Observatory.
I believe so. I might be incorrect.
That's cool.
But there's an 8.1 meter Gemini telescope, and they use ESO's very large telescope, the VLT. Yes. And so I'm highlighting this because the data reduction that they do for their optical stuff, they do data reduction using IRAF, yes. And they do also CCD reduction techniques, for example, taking into consideration bias, flats, and they say, etc., as it's a standard process that we have to do whenever we're doing kind of photometry. NASA / ESA Hubble Space Telescope, the HST, at later times after the burst. So they looked at it 40 days after and 10 months after. It almost seems rehearsed. Wow. There was also the ultraviolet and optical telescope for UBA, and aboard the Swift. There it is again. More instruments aboard the Swift. The host galaxy is the other part. So they use the Hubble Space Telescope images to make a model of the surface brightness, to develop then a profile. Then from that, they have this empirical PSF. Oh no, sorry. This first is that, and then they have an empirical PSF that they use nearby stars. Part of the issue is trying to do some resolving. Since they're all different telescopes, they each have their own resolution angles, and which then creates an issue when you're trying to do source extraction and getting counts from your source. Like you're trying to find something that's really close to the galaxy, and I have a picture, the very last image that you'll see, the location of the source in relation to the nucleus of the galaxy. So then they verified the surface brightness using different models. So just to make sure that everything that they do checks out. And yeah. Now, compared comparison with other short GRBs. So the GRB150101B stands out because of its prompt emission and afterglow. There's a graph here, and I'm only going to point some things out. I don't fully understand it, but I can notice differences in the graphs. And very short gamma ray phase. So this, the emission was 20 milliseconds, so it's very short. And it's an order of magnitude shorter than GRB170817, which is 2 seconds. Then here it says isotropic equivalent gamma ray energy release is one of the lowest ever detected by SWIFT. So it's low energy. That's pretty much what I understand from that. They say isotropic equivalent. I'm not 100% clear on what that means, but it seems that they set a distance from where, like a distance to the source or from the source, and then from there they say that's how much gamma ray energy was released if it were a source at that distance. So they can, I think, then compare with other sources.
Yeah, it's like if you're observing here and the source is emitting this way, you have some like solid angle that you're observing. You're assuming that if you move to any other position along that circle and observe that the emission's the same.
The same.
This is
Isotropic, right? It's isotropic, meaning that it's the same from all directions. Yeah. And it's the small graph made big. So here you see the y-axis is in terms of energy. There are two, right? So there's 300 to 500 and 15 to 300. So this is the lower energy and this is the higher energy. And the things that they point out here of significance is that the higher energy, it seems that there's the peak before the lower energy parts. Right? So you see the peak is here on at this time for the lower energy, for the higher energy, but for the lower energy, you see the peak happens here. All those spikes are all the error bars, right? So like here, that's why they look like little towers. And the other thing to notice is here. The x-axis here is energy. And what they point out is that the energy is different from the other one, but
They seem lower than that's what a histogram, right? So that's just the number of observed events at different energies.
yeah. Oh yeah.
So these are rare.
Yeah. So both of these are very low energies, right? Which means then that maybe we've been missing out on other short gamma ray detections. Yeah. So part of this goes back directly to the motivation behind this, that because of the short gamma ray detection that was made along with the gravitational wave detection, it enabled quick localization, which is key for the Kilonova events because they're very short in time scale. The gamma ray itself happens on the order of seconds. Then the afterglow is something, depending on which regime of the electromagnetic spectrum you're looking at, happens within hours, then days, and then months. And so there could be more events like this that have essentially gone unnoticed, mainly because of localization issues. Then, this one's fun. This is the optical light curve. Time scale on the bottom is days. This is luminosity over energy. There's a lot of points, and I didn't get what all the sources were. So I had to make an assumption because the authors don't clearly state, and they don't give a legend of what each of these things are. So they describe it in the paper itself, that the upside down triangles are the 3 sigma limits. So they do describe these here. You see the blue line is the astronomical transients of 2017 GFO, which was the one that was coincident with the GW170817. So this is the Kilonova from last year, and then this one is the one from or the model for 2015. So they say it fits the model, and they say that there should be some afterglow here. I'm not sure where these extrapolated from extras. Okay. And I have a graph of the extras so you can see that too. It's pretty neat. And these are the I'm assuming then that these squares are all the optical and UV and infrared data points. And here they are again. But now you notice this is the X-ray. The gray region was I don't know actually, so I cannot tell you. But these were the data points for X-rays that were collected with Chandra, I believe, and here it is being compared to the event from last year. So they have the same kind of pattern.
This event from 15.
Yeah.
It's far brighter. And if I recall correctly from the paper, it was a few times farther than. No, this is energy per second.
Wait, did you say farther or?
It was farther.
Yes, I did fail to mention that. Right in the title they say Z equals and you put the number. Z referring to the redshift. From redshift you can make you can do a conversion to distance, and the conversion comes out to I forgot what it was. It was either I think it was 400 megaparsecs.
Yeah.
400 megaparsecs. And again, in terms of LIGO, this is still out of reach for the neutron star binary merger. So the one that happened here, can you remind me what it was? The distance in megaparsecs.
40 parsecs.
Okay, good. Yeah. So 40 megaparsecs. That one was within range. We got lucky. Well, the entire event, the entire story that people who know the history know that we got extremely lucky. All right, and the temporal analysis, right? So the earliest follow-up that happened was 1.5 days after after Swift was triggered, and Chandra observations were used to resolve 2 nearby sources. The resolution between the Swift satellite had all the flux combined for the sources and there's 2 sources close to where the event happened. So all the flux was combined, and they tried to remove or separate those using some interesting techniques, right? So there's 2 models that are used to describe they mention them as the 2 leading models used to describe the afterglow evolution of GRB170817A, and one is described there as in the solid line in these graphs. It's a highly relativistic structured jet seen off-axis, and the dotted line, which is a choked jet with a nearly isotropic, mildly relativistic cocoon. So this is talking about the way that the Kilonova happened. Right? I wouldn't be able to tell you specifically what the differences are. I do remember that one of them means that there's the cocoon, there's like the ejected mass that is through the choked jet, is the energy that's being radiated out from the collision. So there's that jet gets stuck inside the mass that's all around there. So and the highly structured jet, or the highly relativistic structured jet, is if the jet is not choked. In other words, it has enough energy to actually shoot those particles out through that mass. Yeah. Okay, so I do remember. Yes. And so what they did is they used both models that they used for the GRB170817 for the GRB150101B. Right. And so those are the fits that you get here. But that's too small, so let me zoom in. So X-ray flux and the models. And I think it's pretty crazy that just in terms of points and fitting, right, that they only have 2 points, right?
Fitting models with 2 points. I'm pretty sure that you can fit pretty much any model.
Yeah, but it agrees with both models, and that's the impacting part.
I guess if anything, you said that these are the 2 leading models, so maybe these 2 points ruled out.
The other ones, yeah, it could
They
very
didn't
well
even
be.
fall on the lines, maybe.
It very well could be.
Yeah, but if you go back to one slide, one more, sorry. If you
Done?
here we
Yes,
have an
sir.
upper limit on
Yes.
the one day, so this favors if you use the second model, which was the dominant one, this upper limit rules out at least part of those models. Yeah, basically.
Yes. Oh, I see. Right. The upper limit. They did make mention that there is something. One thing here, the Swift data is what's the word? Most of the contribution for these data points are the galactic source. So which is this right here, the gray bar. So, but aside from that, they also made another point saying that there is an issue with one of the models saying that there's something about the energy levels that you get nothing and it's just flat. I can't tell you specifically more because I don't know that much more about it. Then the spectral analysis. And the fitting here is a simple parallel where you have the flux being proportional to the frequency and some spectral index. And they specify the spectral index on the paper. It's like a number. And here is what the spectrum from the 2017 event would be. But it's multiplied by a factor of 2, so you can see it. And, also, it's not just so you can see it, but you can see that they line up with the data point from the 2015 event. The upside down triangles, again, are the upper limits. Now, the picture of the galaxy and the location of the source. There it is. And that line up there says 5 arc seconds. This is, This is the image that they were using from the Hubble Space Telescope to then make their profile, right, for this part of the sky.